Section 5.2, we're going to look at a concept called the definite integral, which is basically going to formalize what we talked about in 5.1. Remember, the idea that we looked at in 5.1 was finding the area under a curve based on areas of rectangles. So if we have some function y equals f of x that looks like this, from y equals a, or x equals a rather, to x equals b, and we wanted to find the area under this curve, what we did is we said, all right, we're going to take a certain number of subintervals, say n subintervals, whatever that number happens to be in, and we're going to let a then be x sub 0, then we'll have x sub 1, x sub 2, and so on. B is going to be x sub n. The one before b will be x sub n minus 1. Alright, so this is just a general thing here. And then we said, alright, we'll make some rectangles then, and we can either do it by taking right endpoints, left endpoints, or midpoints, and in fact we can actually do it taking any value of the function, so, or any x sub I on the interval from x sub 0 to x sub 1. Now let's just go ahead and take right endpoints, and so we can see then that we get these rectangles, and so on, and that the area of these rectangles, which is easy to compute, the area of each individual rectangle, because it's just going to be the function evaluated at the right endpoint, that's the height of the rectangle, times the width. Now remember what the width is. The width is delta x, which was b minus a over n. And then we took the f of x sub i's for each of these things, and so we said then that the sum of each of these, f of x sub I going from 1 to n times delta x, gives us an approximate area underneath that rectangle. And then we said, well, actually, if we take n to be smaller and smaller, or sorry, actually n to be bigger and bigger, so that delta x is smaller and smaller. If we take more and more subintervals, we get a better and better approximation, as we have seen. So if we take the limit as n approaches infinity of this sum, then that gives us the area under y equals f of x from x equals a to x equals b. Now the portion of the sum there that we looked at, this right here, oops, this is what's called, actually let's come up here, this is what's called the Riemann sum. So that's the Riemann sum. Let me write that again. And that's one of the things we can use to compute this area. So what we're going to do then is we're going to say that the definite integral is going to be this right here. We're going to define the definite integral to be that. So we will say that if f is a continuous function, just on definition 2 on page 354, f is a continuous function defined on x goes from a to b, and we divide it in subintervals, we will define the definite integral of f of x from a to b, which is how we read that. The definite integral of f of x dx from a to b is going to be equal, just exactly what we said, the limit as n goes to infinity of the sum I goes from 1 to n. I'm just going to use right endpoints, f of x sub I, not d, but times delta x. This is just taking the right endpoints of each of your subintervals. Now you could also, as the book points out, you could also say it's equal to the limit as n goes to infinity of the sum I goes from 1 to n, f of x sub I minus 1 delta x, because now when I is equal to 1, you're starting with x sub I minus 1, x sub 1 minus 1, x sub 0. So you're taking, in that case, you're taking your left endpoints, x sub 0, x sub 1, and then your last one, and so on, is going to be a height of x sub n minus 1. That would give you your last rectangle. So there's your left endpoints also. But that's also exactly equal to this integral function, the integral from a to b f of x dx. And what this gives you then, this just gives you a number, because it's going to be the area under that curve. This is going to be the area under that curve. We call f of x the integrand, so f of x, the function, is called the integrand, and then the a and b are called the limits of integration, a being the lower limit and b being the upper limit. Now again, this is the area under the curve. Now that's if f is a positive valued function. If f is a negative valued function, which is to say if f takes on negative values on that interval from a to b, then we can think of the integral from a to b of f of x dx as a difference between the positive values, the areas above, minus the areas below. Okay, so there's a nice picture in the book there if you're looking at some function from a to b f of x dx, and maybe it does something like that. Well, then all this down here, this is your blue that you see in the book here, here, and here. This will count as basically negative area. So you could have a negative integral, and the stuff up here will count as positive. So, in other words, this is positive here, and negative here. Now the overall value could be positive or negative. Let's look at an example. Okay, so here we're looking at the function y equals f of x equals 2 times the cosine of x. And what you can see that the actual net area, we're going from x equals 0 to x equals 6. So looking at the integral from 0 to 6 of 2 cosine of x. And again, that's going to be the area, but we have some positive areas here in yellow, some negative areas here in blue. It says that the actual net area, the total net area, is negative 0.55. The approximate area based on these rectangles with a left endpoint and 5 intervals is negative 0.44. Now let's see what happens as we increase the number of intervals here. We're getting a better approximation. We still have a negative area overall, negative net area. So 20, there's 50 subintervals. You can see we're getting better and better. Now we're accurate to 2 decimal places. Now we are almost accurate to 3 decimal places. Still not quite, but we are definitely getting closer and closer here for 150 subintervals. Alright, but we do have an overall negative net area. In other words, the area here in blue is slightly larger than the area here in yellow. It's larger by 0.55883 and so on, so we count that all as a negative area. And so the integral from a to b, integral from 0 to 6 of 2 cosine x dx, well, that's approximately negative 0.55883. This is the integral from 0 to 6. Now, this has nothing to do with this picture above it. It's not the same picture. But the point we were trying to make earlier is that it doesn't matter if we use the right endpoints, left endpoints, or midpoints. If you use the right endpoints, and say start with 5 subintervals, well, here we have an approximate area of negative 0.53, but the actual net area is, again, negative 0.55 from 0 to 6, 2 cosine x. If we increase the number of subintervals, we get better and better approximations. All right? And if we do midpoint, we should get the best approximation yet. If we start with 5 subintervals for the midpoint value, there again we're taking the function value, and we'll talk a little bit more about this in a second, the function value here at the halfway point of our subintervals. Now you can see we should get pretty good approximations right away. There's 10, there's 20, there's 50, now we're at 0.55. There's 100. Now we're actually right to 3 decimal places. We didn't get that accurate with the left or right endpoints. Here we're actually accurate to 4 decimal places. So the midpoint is usually going to give you the best estimate of your areas under a curve. And you can see then if we change this thing, it's possible we could have an overall positive area. Like the integral from negative 1.9 to 6 actually gives us a positive net area. So the yellow values, the yellow areas here are slightly bigger. There's more area there than in the blue. Alright, so there's the idea of that. Alright, I do want to say something about evaluating integrals. It's a discussion on page 357, and we'll look at a couple of examples here, but we do want to be able to evaluate integrals using the Riemann sum. There's going to be an easier way to do it you're going to learn very shortly, but for this section there's going to be using Riemann sums. Now there's some basic sums that we'll need to know in order to evaluate some of these integrals. If we add up I going from 1 to n of I. Now what does that equal to? That's equal to 1 plus 2 plus 3 plus and so on all the way up to n. Depending on what n is, we can get the total for this sum. It's the value of n times n plus 1 over 2. Alright, then we're also told equation 5 on page 357, if we add up the i's from 1 to n of I squared. So what's that going to be? 1 squared plus 2 squared plus 3 squared and so on, all the way up to n squared. That's how we read that Riemann sum. That's going to equal n times n plus 1 times n plus 2, all of that divided by 6. And finally, if we add up I going from 1 to n of I cubed, which of course would be 1 cubed plus 2 cubed plus 3 cubed and so on up to n cubed, that total is going to be n times n plus 1 over 2, that quantity squared. Alright, now the other formulas you can see there for 7, 8, 9, and 10, I'll let you look at those in the book yourself, as you already have. That in particular, if you look at number 7, it just says that if we add up I going from 1 to n of c, what's that? Well, it's c plus c plus c plus c n times, that's just going to be n times c. So that certainly makes sense. And the other ones I think will make sense as well. So with that in mind, with those rules in mind, let's go ahead and look at an example. This is going to be similar to a problem out of your homework where I want to evaluate, let's say, from, I don't know, from 1 to 3 of x squared plus 3x minus 1 dx. Now, another property that we didn't talk about, but which I just told you to look at was, let's see, the one that says we can split this up. Well, actually, let's go ahead and use the instructions here. This is like number 22 out of your book. The instructions here say that we want to use equation 3 to evaluate this. Now, equation 3 says that the integral is equal to the limit of the Riemann sum. So this is going to be the limit as n goes to infinity of the sum I going from 1 to n f of xi delta x. Now we have to figure out what f of xi is and what delta x is. Well, we're going from 1 to 3, so delta x is going to be b minus a. 3 minus 1 over n is 2 over n. Now, what about our x's? Well, x sub 0 is 1. Remember, that's always our starting point, a. X sub 1, what's that going to be? Well, it's going to be 1 plus a delta x. What's delta x? It's 2 over n. X sub 2 is going to be 1 plus 2 delta x's. So 2 times delta x, which is 1 plus 2 times 2 over n. X sub 3 is going to be 1 plus 3 delta x's. That's 1 plus 3 times 2 over n, and so on. And what we're going to get then, if we generalize, is that x sub I is going to be 1 plus I times delta x, or 1 plus I times 2 over n, or 1 plus 2I over n. Okay, so now we have then that the integral from 1 to 3 of x squared plus 3x minus 1 dx is equal to the limit as n goes to infinity of the sum I goes from 1 to n f of x sub I. Now x sub I, we just said, is this. That's 1 plus 2I over n times delta x, which is 2 over n. Okay, so what's that equal to? Well, that's equal to the limit as n goes to infinity of the sum I goes from 1 to n. Now, what does f of x equal? F of x is all this. So this is going to be 1 plus 2I over n squared plus 3 times 1 plus 2I over n minus 1. So that's equal to the limit as n goes to infinity of the sum I goes from 1 to n. This is all times delta x, don't forget that, which is 2 over n. Got to bring that down there too. So what do we have? When you square this out, you get 1 plus, it's going to be what? 2 over n plus 2I over n is going to be 4I over n plus 4I squared over n squared plus 3 plus 6I over n minus 1. Okay? Times 2 over n. So far, so good. Isn't this fun taking definite integrals? It'll get easier, I promise. So this is equal to then the limit as n goes to infinity of the sum I goes from 1 to n. Let's combine like terms. We have a positive 1 and a negative 1, so those go away, and we just left with a 3. And let's go ahead and put our constant in there first. Let's see, we have 4I over n plus 6I over n. That gives us a total of 10I over n. And then we have 4I squared n squared. 4I squared over n squared, that is. All that times 2 over n. So this is equal then to the limit as n goes to infinity. Now the 2 over n we can just bring out front because there's no i's in that. So I have a 2 over n times the sum, I goes from 1 to n, of 3 plus 10I over n plus 4I squared over n squared. Okay, now what we can do here is we can split this Riemann sum up with the properties that are in your book on page 357. The sum of two things is well, we can split those up. So we have the limit as n goes to infinity of 2 over n times the sum I goes from 1 to n of 3 plus the sum I goes from 1 to n of 10I over n plus the sum I goes from 1 to n of 4I squared over n squared. Okay, so all we did is we just added those things up separately. Alright, so now we're just about ready to start evaluating. This is the limit as n goes to infinity of 2 over n times. Now the sum I goes from 1 to n of 3. Remember, that's just going to be 3 added together n times, so that's just 3 times n. That was using this property up here. Yeah, this one right here. The sum I goes from 1 to n of a constant is just n times that constant. Okay, so far so good. Plus, here what I'm going to do is I'm going to take a 10 over n out times the sum I goes from 1 to n of I, plus here I'm going to take a 4 over n squared out times the sum I goes from 1 to n of I squared. Again, since there's no I in those terms, we can factor that out. The only thing that's changing is I. So we have the limit as n goes to infinity of 2 over n times a quantity of 3n plus 10 over n times, let's see, the sum I goes from 1 to n of I. Remember, that was one of the ones we looked at. That's this one right here. It's n times n plus 1 over 2. So this is n times n plus 1 all over 2 plus 4 over n squared times the sum of I squared, which, if you remember, is right up here. It's n times n plus 1 times n plus 2 over 6. So it's n times n plus 1 times n plus 2 all over 6. Alright. Let's see what we can do here now. Well, we can distribute this 2 over n through, so we get the limit as n goes to infinity. Let's see, when we take these, the n's divide, we get 6 plus, here we'll have 2 times 10, that's a 20 over n squared times a quantity of n times n plus 1 over 2 plus, it looks like, see, 2 times 4 is 8 over n cubed, 8 over n cubed times a quantity of n times n plus 1 times n plus 2 all over 6. Alright, so now we're ready to take our limit. Now all we have to do is take our limit of all this. So what are these limits going to equal? Well, let's make things a little bit nicer before we do take that limit. We have the limit of 6 plus 20 over 2. That's just going to be a 10 times, we have n squared plus n over n squared here. Okay, plus 8 over 6 is 4/3 times, so I just brought that up there, that's n times n plus 1 times n plus 2 over n cubed. So now we can get our limit. It's actually pretty straightforward. It's equal to, well, the limit as n goes to infinity of 6. 6 isn't changing, it's just 6. Now we have 10 times this limit. Well, n squared plus n over n squared, these go at the same rate. You can think of L'Hopital's rule here. These go at the same rate. So this goes to 1, so we just have a 10. Same thing here. We have an n times an n times an n. That's like an n cubed on top. And so that has the highest power of n cubed. This one goes to 1 as well. And so we have just a 4/3. So we get 16 plus 4/3. Or, what's that going to be? 52/3, I guess. Alright, and there's your definite integral. Now, that's not a very nice thing, but I think it's good for everybody to have to do at least once. Alright, so you'll have to do that, one like that, on your homework. But again, there will be a nice shortcut here for taking the definite integral of a function. And that's a good place to stop. We will look at some more examples and other concepts in the next video.